So for this part of the video, we are going to be doing a catalyst reaction. We're going to be turning ethanol into acetaldehyde and hydrogen in this case. And what we're going to try to show is with the Maxwell-Stefan diffusion equation, what the surface mole fraction of ethanol should be once we proceed it in this reaction with the diffusions that were given, with the temperature and pressures that were given, and the concentration. So in this case, I filled in advance some of the information that we will need for this, and this table is actually the same as the one that we did in the previous problem. I just went ahead and cleared it and updated it for considering our values in this case that we will be using. So, for example, uh, we have this we have this rate constant that we have added to our system. In this case, because we have ethanol, which is producing two products, we have three molar fluxes in this case. So I kind of want to explain the math behind that because I can understand why that would be a little confusing to think because we said in the previous problem that the molar flux for nitrogen in this case, which was a bulk gas that wasn't participating in the reaction, that was just vaporizing the system, didn't have a molar flux, right? This is not the same case. If we had our surface, right, and we had let's say it was ethanol coming into the catalytic surface, that is participating in the reaction, so it has a molar flux. The hydrogen and acetaldehyde are also participating, and they are leaving and have their molar fluxes. So every system has a molar flux in this case. And so the change that I made was for our d of y d of 1 expression. Did I include this yet or no? Let's see here. Which would be the demolar flux. Sorry, I'm just making sure. So we include a third molar flux over here. This is the same Stefan-Maxwell equation that we did for the previous problem, except what I included here was I included the analysis for the third molar flux as well. So just so you can see that, and just so you can see that. So, what is it? What we need to start with is we have to start taking guesses for what the mole fraction of ethanol is going to be in this case, because we only have the Stefan-Maxwell equation. We don't have we don't have the mole fraction of this case of one, two, or three. So where we can start is if we want to proceed with the Maxwell equation that we did earlier, uh, we got to a step where we said that the molar flux equals the diffusion multiplied by what is it? Let me pull it up. This is just me pulling up the previous notes that we had. We said that the molar flux equals the pressure times the diffusivity multiplied by or divided by the gas constant, temperature, and the length of our system. So if we wanted to take a guess for what N1 is, we could say that this is probably the pressure multiplied by the diffusivity. And in this case, for N1, it would be 1 and 2, right? And then this would be divided by the gas constant multiplied by the temperature, which is then multiplied by our change of distance. Should be it. Okay. So ignore all these values for now. These aren't super relevant. So we now have a molar flux, or at least one that we can guess. And for N2 and N3, again, this is going back to the molar analysis. If you look at the reaction, which I have written down here, you have ethanol turning into acetaldehyde, right? So you have C2H6O turning into C2H4O, and then that's plus the hydrogen. So the molar balances check out, and the negative molar flux of the ethanol is inverse and proportional to the molar flux of the hydrogen. and the acetaldehyde because they are molar equivalents with each other. So to kind of explain why these auto-populated with these values. So now we have a guess our uh as to what our molar flux is. However, we still don't really have a proper guess for Y1, which is what the where are you? Which is where this rate constant comes in. If we take the absolute value of N1, actually wait, sorry. This should be negative. Right, this should be negative because it's being consumed in our system. So it's negative. So if we take the absolute value of our N1 and divide it by our rate constant, which is 10 in this case, should get an actual Y1 function, which looks something like this. Now, going back to actually a place that we can start is we can have something that's close to zero point 0.5. When we did this in class, we actually just pulled the previous mole fraction of Y2, which I think was methanol. But in this case, this is a pretty similar type of problem. So for the sake of argument, I am going to say that Y2 also equals 0.528, just for the sake of argument in this case. And now what we're going to do is I'm going to insert this value into Y1. And you can see we're populating some data here. This data and the trends look pretty promising. So here is what we're going to do, because as we go down here, a problem that we encounter is that, oh, hold on, I don't know why I didn't do it like this. A problem that we encounter is that the mole fractions for the ethanol, acetaldehyde, and the hydrogen don't really match with their molar fractions that we were given earlier. For this problem, we said that the bulk gas composition is 60, 20, 20. So there should be roughly 60% ethanol and 20% hydrogen and 20% acetaldehyde, right? Or acetaldehyde. Sorry, my bad. So the fact that they don't look like that once the reaction is complete is concerning for us. So we need to do a summation squared and use Excel solver to see if we can get a value that would allow us to determine what Y1 and Y2 should be for then the final mole fractions to be zero point 0.6 and zero point 0.2, right? So let's see here. We can do some squared. Actually, I should probably explain this math. Sorry. This is left over from the previous part, but I'll explain again really quick. These are simply the last two values. So if I go, this is H2. So these are what should be, yeah, Y2 and Y1's values once we've completed this distance of the full length. And so we're going to try to make these numbers match the molar fractions here. So we're going to take sum squared. Sum squared. I believe it's something like, oh, you know what? No. Here's what I'm going to do. I'm just going to go ahead and do, this is going to be equals sum. Actually, wait, no, this needs to be, this equals this minus that. So I'm going to go ahead and pause really quick. I don't want to do sum squared wrong. All right, so to do the sum squared, we're going to do, let's see here, the latest value. And then we are going to subtract it by the value that we want. And we are going to square this. And then we're going to do the same over here. And then if we add these two together, oh, which is just, this is the sum of square in this case, we get a value that looks like this. So actually, what would probably be better is if we did sum, just to make sure that this works fine. Okay, so we have a placeholder value, and what we're going to use this for is to use Excel Solver to change this, to change y1 and y2 to become our desired values for the mole fractions of zero point 0.6 and zero point 0.2. So hopefully when we use Excel Solver over here, we should be able to, I am, sorry, hold on. Sorry for the sudden stops. I had something come up. Okay, so we're gonna use Excel Solver in this case. So, what we want to do is we want to set our objective, which we said was going to be this sum squared. So that's going to be our adjustable value. We want the minimum of this, and we want this changing by the variables of y1 and y2. And just to kind of make sure that this works as best can, we're going to make sure that these are less than or equal to 1 in this case. Did I do something wrong? But then I get this and this. They're not empty. Hello. That's why we're trying to flip it. It doesn't want to work either way. Okay, I'm going to cancel this for now. Let's see what happens. We want to make non-constraint variables, so let's go ahead and solve for this now. See what we get for y1 and y2. Hey, that does not look too right because these two don't exactly look like the values that we want. Okay, I'm gonna run this. I'm gonna see what the last variables look. Okay. So I was trying to use Excel Solver for a little bit and I could not get it to work. I did some testing on another page and the values were not coming out as they should have. So I went ahead and went to the textbook to try to find what molar values we should be able to use to get what should be our rough equal to our mole fractions in this case, to which if we look, if we set the molar fluxes to 5.36 times 10 to the negative 2, we can see that we get a molar fraction at the very bottom that about emulates the zero point 0.6 and zero point 0.2 values that we were estimating in this case.